In this video, we'll be doing another example of rational functions. I will tell you that this is going to be another optional video. It's talk about wholes. It has some of the same content we have discussed, but it has one little extra thing. So you won't see one of these for points, but you might see it for a bonus on one of your exams that are paper pencil. And so this one is 2x squared minus 5x plus 2 over x squared minus 4. And when you first look at these kind of functions, you may not be able to tell one from the other, but I can, because what I know is I see a common factor, and so I would know not to give this one to you, because this one right here has a hole, even though you may not see it right now, because there's a common factor in the process of reducing it. Now you know it's not going to have a curvilinear asymptote, because those are going to be obvious too, because the curvilinear asymptotes have a degree more than 1 on top than it is on bottom. So remember we did one before with a curvilinear asymptote. That was an optional video as well, and I think that the top was like a degree 4 and the bottom was degree 2, which is more than 1 bigger. And so this one right here, it's not going to have a curvilinear asymptote, but it will have a hole. And that's what he calls it. He says analyzing a graph of a rational function with a hole. Now that's being very informal. The real definition of what a hole is called a removable discontinuity, and that's what this one really is, what it's really called. And so let's begin with this function. So step 1, factor it out, and it'd be 2x minus 1 over x minus times x minus 2 on top, and the bottom x squared minus 4 is x plus 2, x minus 2. So the domain is all real numbers except for negative 2 and positive 2, because that's what makes the denominator 0. Now if you look at this, and when you start in the reduction process, look what happens. The x minus 2 cancels, and it reduces the the rational function, down to 2x minus 1 over x plus 2. So that's what you work with. You work with 2x minus 1 over x plus 2, and the process is exactly the same as what we have been doing. The y-intercept is at negative 1/2, and plot the point at 0, negative 1/2, and the graph has one x-intercept at 1/2. So because 2x minus 1 equals 0, add 1 divided by 2, yep, it's x equals 1/2. So right now what I would do if it was me, I would plot the point x equals 1/2, plot that x-intercept, plot the y-intercept at negative 1/2. So both of those intercepts are really, really close to the origin. One is to the right of 0, and one is down below 0. That's exactly what I would do right now. So now that what they're doing is they're plugging in numbers that are close, and to tell you what that blue part, this is the part that I don't really bother with, and it's letting you know what's going on really close to that. So 1/2, 0 showing a line with a positive slope. So they're testing the point on both sides. So this kind of tells you which way the graph is going after it exits the asymptote. The intercept. So once it leaves the intercept, what he's discussing here is what it does afterwards. And that's been a little bit too precise for what we're trying to do. But you can do that if you like. Now you can read these, and it tells you more so what it's doing in between those. But let's look at the graph. Okay. So we've already established that the vertical asymptote is at negative 2, and we have a horizontal asymptote at y equals 2. Okay? It's because the degree on top, and let's go back and look at the original function again. So it's 2x minus 1 over x plus 2. So if you have that, the vertical asymptote is at x equals negative 2, and you divide their leading coefficient, or using the long division concept that he began with, you'd get 2. So that gives us the horizontal asymptote at y equals 2 and the vertical asymptote at x equals negative 2. We plot those additional intercepts. Notice it's at 1/2 and the one down below it, which is at negative 1/2. Alrighty? So now all that verbiage he had on step 3, all that's basically saying is you got to go through those 2 points together. So you got to go from one point to another point. So all he had to do is say connect those 2 points because there's no x-intercepts in between them. So, which would have been a whole lot easier for him to say that. All right? Now, the question is, right now I'm pretty much done with the graph in my mind. But what he's going to do now is he's going to want to test points like he's always been doing. He's going to want to test a point between like -3. He's going to want to test like -1. He's going to want to test like number 2. He's going to want to test other numbers outside what you already have. And that's what he's doing right here. So he looks at the boundaries and what you got in between. He tests the number -2. He tests the -3. He tests -1. He tests 1 and he tests 3. Okay? So he tests all those points to come up with points that will be on the graph. Those are what he would call additional points, and he shows you right there. Okay? So now you kind of know what the graph is doing. And there it is. That's what the graph looks like. Okay? Now, what I'm saying is, right here is what he's got, what he has, what the graph is doing. Now, I know you're looking at that hole there really quick. There's a hole at that point, but let's come back to that later. I want to show you something else. Let's go back before we get that. Can you see what the graph looks like right there? The graph he just got versus this. Now remember, he went through several other steps to get here. But I know the graph to the left of -2 is going to be that backwards L shape in the second quadrant. Because there are no x-intercepts to the left of -2. So the graph has to be up in that second quadrant somewhere. And into the right side of -2, since you got to flow through those intercepts, it has to be somewhere in that first quadrant down through the third quadrant down below. Now let's go back. So see what the graph looks like there. Now let's look at what his final answer was. And it goes like that. So -3 to 7, and then he got it going through there. Now I know let's talk about the whole. 2, 3/4. Now what he does is we know that those x minus 2 cancels. So we know 2 is not defined. But it's not a vertical asymptote because they canceled out. So what happens at 2 is what we call a removable discontinuity, which basically means you draw the graph, and wherever the graph ends up at, in this case right above 2, 0, right above there, you take a point off the graph and make a hole in it. You remove a point off the graph. That's why it's called a removable discontinuity. Now you're like, how do you know it's at 2, whatever that number is, 3/4, whatever, how do you know that? Well, because if you put 2 in right now, it's going to be 0 over 0. But what you do is you put 2 back into the simplified version of the graph. And that's how you come up with its y-coordinate, that y-coordinate there. So now that is a little bit beyond our scope. And that's why we don't do this particular problem. It's a good problem to think about after you get it and you get the removable discontinuity in there. And as a matter of fact, even in my traditional classes, I don't ever find the exact point, 2, 3/4 or whatever. I just go up there and take the graph and take a point off of it, put a little hole there, and move on. So, but anyway, that's how you find the removable discontinuity. All right. So again, this example is an optional video, and you can look at it if you like. It's good for bonus points if I decide to give it to you as a bonus problem. But you will not see anything like this on your homework that has a removable discontinuity. It's a good one to look at anyway, just to review how to do the other things that are necessary, like the vertical and the horizontal asymptotes. The big thing I'm trying to get across to my students is that make sure that the shape is right. You don't have to do all the point plotting that Solomon is doing here. They're good to have as long as you're accurate. And then once you test -3, what he did when he tested -3 and got 7 up there, then you're kind of, yeah, okay, it's going to be up there in that second quadrant, having that backwards L shape. But the point -3.7 is not the important thing. The important thing is knowing that it's up there in the first place. So, and I know it's up there because I know I don't have any x-intercepts to the left of -2. So it's got to be up there. So, so there's shortcuts more than what Sullivan is showing you here. But if you're comfortable with his way of testing points, go for it. I'm just saying it's very time consuming if you choose that way. So anyway, if you have any questions on this one, remember it's optional video. There won't be anything with holes on it. You ask me a question, I'll call you up, or I will send you an answer through email on MyMathLab. And you have a good day.